In this video, we present our work on reactive in-air clothing manipulation using confidence-aware dense correspondence and visuotactile grasp affordance. Our key contributions are custom simulated shirts for correspondences across different shirt geometries, confidence-aware pixel-wise dense correspondence for shirts both crumpled on a table and hanging in air, visuotactile affordances to find good grasp regions, and finally, we combine correspondence, affordance, and tactile sensing for reactive, task-agnostic in-air garment manipulation. We'll start with our parameterizable simulated cloth model. We train this network in simulation with a custom dataset generated in Blender. Our shirts have different colors and textures, U-necks and V-necks, differently sized collars, and bodice dimensions, can be short sleeve or long sleeve, and feature details like seams. We found that the shoulder hem provided crucial context to help distinguish sleeve ends from bottom ends. We're able to include all these features because we had scalable meshes, so each vertex on the mesh always corresponds to consistent points without an intermediate skeleton. We also randomize cloth dynamics parameters. Here are some examples from our simulated dataset that has 3,000 hanging images and 1,500 table images. The table dataset is in line with the level of difficulty of similar works. No one, however, has published on dense correspondence and hanging garments before, let alone a network that can find correspondences both in air and on a table. The shirt is highly occluded in most of these cases, and it's hard to find distinguishable features, even for a human, highlighting why having a low confidence option is so important. We've covered our simulator. We'll now move on to how we train dense correspondences. Here we have a deformed shirt and a canonical shirt, and we want to learn pixel-wise correspondences between them. During training, we query a point on the deformed shirt, and we're able to get the corresponding pixel match in simulation. We put these into a dense correspondence network that we're training. The output of this network is a dense descriptor for the shirt where every pixel is mapped to a d-dimensional embedding. Traditionally, these networks are trained with contrastive loss. Here we find pixel matches between deformed and canonical images and structure the loss to decrease the distance between matches in descriptor space. Simultaneously, the network finds non-matches and pushes them further apart. For distributional loss, we have a target distribution that's a multimodal Gaussian with modes at symmetric match points. We get the probability estimator by taking the softmax over negative distances in descriptor space. Then we train the model by minimizing the difference between the target distribution and the probability estimate. Distributional loss is advantageous because we can encode symmetries and have a built-in confidence estimate, both of which are essential for in-air garment manipulation. Now that we know which shirt regions we want to grasp with dense correspondence, let's determine if we can actually grasp them using visuotactile grasp affordance. Our grasp affordance network finds good grasp regions for a hanging shirt using only side grasps. We provide a depth image of the shirt as input and get a heat map showing graspable regions as an output. Red regions correspond to where we can actually grasp. We first train in simulation and fine-tune on the robot. In sim, we can explicitly check criteria including, is the point reachable? Will the gripper collide with fabric? Are we grasping 2 layers of fabric or less? However, we see issues with sim-to-real transfer because shirts in real life have a wider range of material dynamics. Therefore, we fine-tune on the robot using a tactile classifier to supervise grasp success. Here we show the data collection procedure for fine-tuning. The visualized grasp affordance shows predictions from the model trained in simulation and selected grasps based on that affordance to improve efficiency of grasp selection. We also visualize the results from our grasp classifier network that we use to supervise the success of grasp attempts. In simulation, we're able to label affordances for the entire image. On the robot, we evaluate a single pixel at a time. We fine-tuned with over 8,000 grasp attempts, all supervised by the grasp classifier. Here are examples of our fine-tuned network compared to the one trained only on simulated images and one trained on our 8,000 real grasp attempts. We found that our network from simulation was too conservative, often missing important points on the bottom of the shirt, while training only on real data resulted in overconfidence in unexplored areas. Finally, let's combine these components and introduce our reactive in-air garment manipulation system. Breaking down our framework, we start by picking the shirt from the ground using dense correspondences and tactile sensing to ensure grasp success. We pick a second point in air using dense correspondence, but now we include grasp affordance to ensure the point is actually graspable. Once again, our tactile classifier lets us know if the grasp was successful. If the grasp didn't get enough fabric, the robot tries again. Once we have 2 grasps, we can tension the shirt with tactile feedback. And finally, we can either fold or hang the shirt on a peg. Here's a step-by-step example of our in-air dense correspondence plus affordance system for a single grasp. So in this case, we're querying a point on the end of the sleeve, and this is the best correspondence match according to the network. The network is right about that point. We're going to iterate through a video where the network decides whether to grasp its highest confidence graspable point or rotate to a new viewpoint. We'll be visualizing the best match pixel, grasp affordance, correspondence to the sleeve where darker red points are more confident, and correspondence masked to points that are actually graspable according to affordance. We start with relatively bad affordance for the sleeve, since the surface normal isn't aligned with the gripper. As we rotate, the sleeve moves to a better position for grasping, and the network also becomes more confident that that point is actually a sleeve. Once a high correspondence point has good affordance, the robot can go in for the grasp. Let's go through this in a state machine format. In order to find a grasp point, we need to check for confidence. Here we're checking for correspondence confidence, grasp affordance, and if these two are high enough, we attempt the grasp and only move on if the tactile classifier confirms grasp success. Otherwise, we rotate and try again. Instead of looking for the same grasps each time, we allow our network to dynamically choose between different folding strategies depending on which grasp it's most confident in. The first grasp is attempted on the table, but if that fails, that can also be done in air. If the first grasp is a shoulder, the second grasp should also be a shoulder. If the first grasp is either a sleeve or a bottom, then the second grasp can either be a sleeve or a bottom, depending on what's visible and graspable. Once we have 2 points, we can tension and fold. If we can't find a good grasp at any stage, or if the cloth slips, we can return to a fallback option and start over. If we can't find a good table grasp, we just grasp the highest point. If we can't find a good grasp in air after rotating a full rotation, we grasp the lowest graspable point to help unfurl the cloth. We tension using tactile shear estimates by tracking the displacement of the markers on the gel surface of the fingertips. This closed-loop step is useful for generalizing manipulation to shirts of different sizes and to different grasp points on those shirts. Here's a full example of folding, where we show the tactile classifier after grasping from the ground. We show correspondence, affordance, and correspondence masked with affordance, tactile classification from the grasp attempt, tensioning, and folding. Here's a compilation of other successful folding videos. There's a variety of shirt geometries, including a long sleeve shirt in the top right, different material thicknesses and dynamics. You can see different folding strategies, as well as grasps being attempted and the tactile classifier informing the robot to try again. In addition to folding, we can also use the same correspondence and affordance for hanging. This time we look for a shoulder or a collar point on the ground and look for a collar in the air. Then we can bring the shirt over to the peg, pull down, and let go. Note that we can also do these tasks on long sleeve shirts. We can also use our dense representation for other planing modalities. For example, learning from human video demonstrations. We track hand skeletons and classify gestures, looking for frame transitions to 2 grasping hands. From our keyframe, we can go back a couple of frames to get our unoccluded query point and calculate a probability heat map using our network and get the best pixel match. We do this with the other point as well. Ultimately, we present a reactive visuotactile system for garment manipulation that integrates dense visual correspondence, visuotactile grasp affordance, confidence-aware planning, and tactile feedback. Unlike prior work that was constrained to tabletop picking or reliant on flattening, our system supports in-air garment manipulation by searching for correspondences directly from highly occluded states, enabling more flexible, human-like manipulation.